This is a whole new ballgame. Logarithms is a different type of function. So you have linears, you have quadratics, you have exponentials, you have rationals, you have radicals. Now you have logs. Okay? Even the symbol of log, unlike the others, where you actually knew the radical symbol, logs is just brand new right from the get-go. But it's very closely related to exponentials. We're going to find that exponentials and logs are inverses of each other. So just like squaring and square rooting are inverses of each other, you use them to kind of undo each other if you're solving. Logs and exponents are inverses of each other. So the way I typically try to present this so that it makes sense is when you think about a foreign language, like bonjour really means good day. Good day. Well, hello is yes. So when you hear bonjour, and maybe that's a little too mainstream, but that means, let's talk to my other Frenchies, because that's what I took. Right. When you guys hear that word, if you are a French person, in Spanish, whatever, we could do our own for that, but I don't know as many words. You see that, but your mind processes the English version of that, right? So here's our foreign language. We have no idea what that means, right? The translation to get this into something that we do know, and let me tell you how this would be read. This is log base b of x. Log base b of x equals y. That's the foreign language. What it means is that base of b raised to the other side equals whatever's in the middle. So your base of your log becomes the base of your exponent. That's a nice transition because they're both the bases. But you take the base of your log and you actually raise it to the other side, and it equals what's in the middle. It's not just crossing out the logs. It's not b to the x equals y. It's b to the other side equals x. So when you see something like that, you're going to think this. Just like if you are in French and you see the word parlay, you immediately think about the English version that makes more sense to you, correct? Okay, so when we're evaluating this, some people call this the what power function. And the reason is because, for something like this, in exercise 2, where we are evaluating, we're trying to figure out, and Jason, were you listening to me? How do you read this? Who listened to me? How do you read that? Bella? Not raised to the 8th. Nope. Nope. Sierra? Right. Log base 2 of 8. They want us to evaluate and figure out, well, what does this equal? We're essentially trying to figure out what does that equal. So the translation, so it's a language that we know, is that our base of 2 raised to the other side, which is some question mark, equals 8. So people call it initially, I think it's a nice interpretation of it, the what power functionality. So you're really looking for 2 to what power gives you 8, and when you translate it, you can kind of see that, right? And so what's the answer? 3. Log base 2 of 8 is 3. And so you don't necessarily need to write that every time. 4 to what power gives you 16? 2. 5 to what power gives you 625? You gotta check it. 4. It's 4. Stop yelling at me, Bella. 10 to what power gives me 100,000? 5. Oh, I know you guys love fractions. 6 to what power gives you 1 over 36? I'm going to let Owen answer this. -2, right. 6 to the negative second power gives you 1 over 36. So log base 6 of 1 over 36 equals -2. 2 to what power gives me 1/16? Let me go with Sierra with an S. Correct. Jason? Read that to me in math language. Good job. G. 5 to what power is the square root of 5? We know fractions make negative exponents. Radicals are what kind of exponents? We have a flashcard that says the b root of x to the m is the equivalent of x to what power? M over b, right? So the square root of 5 is the same as 5 to the 1/2, right? So 5 to what power is 5 to the half? 5 to what power is 5 to the half? What would the question mark be? 1/2. So this is your question mark, right? So 5 to what power equals the square root of 5? And when you take the square root of something, that's the same as raising it to the 1/2 power. And so the thing that fills in your question mark is 1/2. Does that say that? What do you think that says? The cubed root of 9. Not 3 radical 9, Haley. 3 radical 9 is that. Cubed root of 9, I think, is what you meant. Okay. That's a big difference. Are we good with that? 3 radical 9 versus the cubed root of 9. So this is log base 3 of the cubed root of 9. We're going to pretend that's a 3. So essentially we're trying to figure out what that equals. So 3 to what power equals the cubed root of 9. And so 3 to what power equals 9 to the 1/3. Now we can do like our common base stuff from yesterday, because 9 is the same thing as 3 squared. Right? Power to power, what's 2 times 1/3? 2/3. And so what's the question mark equal? 2/3. So that answer is log base 3 of the cubed root of 9 is 2/3. Okay? So you're going to want to remember this translation. The base raised to the other side equals what's in the middle. And you also want to, just for like casual, just answering it quickly without having to translate necessarily. Sometimes we'll have to translate base to the other side, but thinking of it as the what power function can also be helpful. Okay. So this is not going to be a nice number. Therefore, they're not asking us. They're saying between which 2 consecutive integers must this lie? So we want to figure out essentially the value for this. So 3 to what power equals 40? It doesn't work out beautifully, right? Nothing exact is going to get us on 40. But we do know that 3 to the first is 3, 3 squared is 9, 3 to the third is 27, 3 to the fourth is 81. And 40 is between these two, correct? Right? Our answer, therefore, is going to be an exponent between 3 and 4? Probably closer to which one? 3. So probably like a 3.2 or a 3.3-ish. It's not going to be even a... So like if I did 3 to the 3.2, that's a little bit short of 40. 3 to the 3.3, still a little bit short of 40. 3 to the 3.4 is a little bit too high. But is it closer to 3.3 or 3.4? 3.4. So maybe I would do, but 3.4 is too much. Maybe I do 3 to the 3.39. Getting smaller. 3 to the 3.37. Did it work exactly? Oh, we're getting better. So it's a little too high, so maybe I'll do 3. But anyways, you get the point. That was just more of a challenge. There's going to be a way for us to solve that exactly, by the way. We're between 3 and 4. All right, new rule. Couple things in math. If you just have 5 plus x, how many x's do we know that there are? Right, so we just assume that's a 1. If you just see, let's say, x, and they don't write a power, how many do we assume there are? 1. If you just see a radical over an x, what root do we assume we're taking, even though it's not written? Square. So there's different places in math where we assume different things, right? If you have an equation of a line that's y equals 5x, what do you assume the b is? No, you don't. 0, right? So we assume, sometimes we assume 0, sometimes we assume 1, sometimes we assume 2. Well, here, if there's no base, you assume 10. And there is a log button on your calculator. It's right there. But if you hit that, it's when you just do log of something, there's no little base thing that shows up. Your calculator is assuming it's 10 when you use that log button. Okay? So you can always insert it. So log of 100 is the same as log base 10 of 100. And Angie, what do you think that equals? Correct. Did you do that in your head or did you do that on your calculator? Okay. And this one is 10 to what power gives us 1 over 1,000? Eric? Yep, -3. And this is 10 to what power gives us the square root of 10? Chloe? 1/2, right. Because the square root is the same as 10 to the 1/2 power. Good, good, good. Okay, so we assume the base is 10 if we don't see one specifically written. Capiche? How do you like your new language? Is it easier than French? Easier than Spanish? No. Oh boy. If the function, so we're already talking about graphs. We have no idea what the graph of this looks like yet. We'll get to that. But we're talking about graphs. Pretending it was graphed in the coordinate plane, which of the following would represent its y-intercept? How do you find a y-intercept? X equals 0. So y equals log base 2 of 0 plus 8 plus 9. So let's talk order of operations. What would you do first? 0 plus 8. We'll turn it into log base 2 of 8 plus 9. What would come next? Do it like evaluating the log, right? Log base 2 of 8. 2 to what power gives you 8? 3. And so your answer is 12. You'd have a tough time graphing that on your calculator because if you go to y equals and you type log it doesn't give you a base of 2. It doesn't give you a base option at all. It's just log. So what base is your calculator doing again? 10. So we'll talk about that at a later time. All right. I said in the beginning, exponentials and logs are very closely related. They're inverses of each other. So as far as when we solve things algebraically, we will use logs to undo exponentials, and we will use exponentials to undo logs. We've already been doing that. To undo the log, we change it to an exponential. Okay? And vice versa, we will have to kind of solve some of those ones that I talked about right before I put your homework away. To undo the different base situation, we will eventually use logs to kind of get those exponents out of there. But that's all to come. So to kind of tap into the relationship between the two, they are inverses of each other. So if we think back to inverses, here are all the points on your exponential equation, 2 to the x. How do we get the inverse graph of something? Switch the x's and the y's. So we would kind of flip all of those to graph the log function. And we're going to do that, and they drew this in there. Why? Because in inverse functions, that's the line of reflection. So the other one's going to kind of come out this way, which we'll see in a minute. Before we get there, is this exponential function 1-to-1? Does it pass the vertical line test? Yes, passes vertical line test. Does it pass the horizontal line test? Yes. So passes vertical line test and the horizontal line test, which means yes, it is 1-to-1. And when a function is 1-to-1, that really just means its inverse will also be a function, correct? So when we flip all these points, the inverse, it will also be a function. So let's start flipping. So rather than -3 1/8, we're going to have 1/8 -3, 1/4 -2, 1/2 -1, and so on. Some of these points are going to be pretty tricky just to graph just because they're so teeny tiny, but do your best with it. Like an x coordinate of 1/8 is barely off the y-axis, and then down 3. 1/4 is not much further off the y-axis and down 2. 1/2 is -1, 1 0, 2 1, 4 2, and 8 3. Good. So the equation, our original equation was y equals 2 to the x, which I'm going to write down in part D. What is the first step to writing an equation's inverse? Switching the x's and the y's. So there's your original, and our inverse would start with x equals 2 to the y power. Right? Does that make sense? So if I were, now this is something tricky, we haven't done this yet. If I were to go backwards from exponential into a log format, where does the base of the exponent go in the log part? The b here goes as the base of the log, right? So if I were going backwards, it would be log with a base of 2. The base of the exponent goes back to the base of the log. the exponent of the base is where in the log equation? On the other side of the equal sign. So that exponent of y is on the other side of the equal sign. And then the x that was by itself is what we're taking the log of. You follow? So this x that was by itself is what we're taking the log of. I think it's easier to go from log back into exponential because I can just say my base of 2 raised to the other side equals x. But this and this are the same thing. That's like bonjour, that's like good day, right? They mean the same thing, just written differently. So what we get out of that is here's our original function, here's our inverse function. Y equals an exponential, y equals a log, and you can kind of see that they are inverses. Does that make sense? Okay. Now, let's go back quickly to exponentials because this is important. What were the key features of our exponential function parent graph? Where's the asymptote? Y equals 0. Where's the critical point? What's this one? What are the coordinates of the y-intercept? Nope. 0, 1, right? If I plug in an x of 0, 2 to the 0 power will give me 1. 0, 1. And the other critical point was 1, comma, whatever the base was, right? Which is 1, comma, 2 in this case, right? If I plug in an x of 1, 2 to the first power gives me 2. Good? Jack B. Morning. Bonjour. Okay. So if we look at our other graph, in inverses, all things x's and y's flip-flop. So if on our exponential graph we had a y equals 0 asymptote, what's the asymptote of our log graph? X equals 0, the other axis. So we have an asymptote of x equals 0. And if we had a point 0, 1, what's our point in the other one? 1, 0. So what used to be our y-intercept with an x of 0 becomes our x-intercept with a y of 0. Follow? All things flip. And look at your graph. 1, 0 is your x-intercept. And then this was technically, I'll just put it in like quotes, 1, comma, b. Right? Just our base was 2. This one is going to be b, comma, 1. So 1, 2 becomes 2, 1, which is 1, comma, whoops, did I say that right? 1, 2 becomes 2, 1. 1b becomes b, 1. And look at your graph. We have the point. Do we have the point 2, 1? Yeah, right here. 2, 1. Good? So basic intro to graphing there as well. But the translation for tonight is like the big takeaway. I see Santa, I see the Grinch, and I know there's an elf in the room. What can the rest of you say for yourselves? Scrooge? Is that what you're all going with? You like that, Haley?